Welcome to let's say, the first session of second half. So today we have Mr. N. Venkatesh San from Silicon Lab. Sir has over 35 years of industry experience, during which he has worked in semiconductor design, communication systems, avionics, embedded systems, wireless technology, and other areas. Sir holds a master's degree in electrical engineering from Indian Institute of Technology, Madras. He holds 22 US patents, contributes to IEEE standards development, and he is also a fellow of Indian National Academy of Engineering. Currently at Silicon Labs, as a part of the company's Silicon Labs University initiative, Sir works with internal R&D team, the industry ecosystem, and universities in supporting the development of innovative semiconductors and IoT solutions. Sir, welcome to the NITK and welcome to this session.
Thank you. Sure. Okay. All right, so thanks for staying on after lunch for this. I think you've been having a nice set of different perspectives over the last 2-3 days. You know, the topic of this workshop is AI-driven, secure, critical infrastructure, right, if I'm not wrong. So I think I've seen from the workshop topics that everyone has taken one word from this and spoken about it. AI, okay, then secure, infrastructure, and so on. So I have taken the word secure. And I wanted to give a perspective on security at the smallest possible device level. Every device is now a connected device, and every device needs some kind of secure communication and secure operation. So that's what I'm going to talk about. So I work in Silicon Labs. Silicon Labs is the world's leader in IoT wireless. Some people may ask, what is IoT wireless? You know, there is a lot of different kind of wireless spectrum available. Now the word spectrum is very important business-wise because people have bought spectrum for a lot of money. Jio and Airtel have paid lakhs of crores of rupees to get spectrum so that they can give you cellular coverage. Now, luckily, I mean, not everything needs expensive spectrum. There's a lot of bands which are freely usable, and they're called the ISM bands. The Wi-Fi, Bluetooth, your RFID, all of them use freely available license-free spectrum. And in all the license-free spectrum areas, 800 megahertz, 2.4 gigahertz, 5 gigahertz, in all of those kind of wireless communication, we are the leader. So we provide solutions for Bluetooth, Wi-Fi, Thread, Zigbee, Z-Wave, Wi-SUN, so many different protocols we provide. And we actually enable products like these, like smart thermostats, smart switches, smart light, smart locks, medical appliances. You know, you take a measurement, it immediately gets transmitted to the hospital network. Then you have factory automation, you have security, smart meters, energy conservation, smart city networks, so many areas in which you need wireless communication. We provide the wireless microcontroller device at the semiconductor level. And that's what I'm going to talk about today. Okay, so we are headquartered in Austin, Texas, and we have about 2,000 people worldwide. The biggest center for Silicon Labs is in Hyderabad. That's where we come from. I have my colleague Jackson also here. Okay, so we come from the India office of Silicon Labs, and we have offices in Singapore and in many cities in Europe and in Canada and so on. All right, so our market is the IoT. IoT is a term for any connected device, and today all devices are connected, whether it's your refrigerator at home, your TV, your washing machine, your smart light bulb, smart blinds, everything today talks to the outside world, just like every person today is on the internet and has been on the internet. Okay, so as a communication link, we use the internet maybe more than we use physical medium, right? Similarly, devices are also on the internet. Every device is on the internet. If you go on a highway, the smart tag reads your car and deducts the money and then sends you out without any problem. If you go to the airport here, you can use DigiYatra, the face recognition system captures and then it communicates with the servers to get all the relevant details of your travel, and everything is authenticated. So all devices are connected. And what is the structure of a connected device? You have the device itself, okay? So you have the device itself, which consists of sensors and actuators. Actuators are output devices, like turning on a switch, turning on a motor or something. Sensors are input devices. Then you have a microcontroller. Today we cannot imagine doing anything without a microcontroller. So how many of you here are electronics background? Okay, that's good. And how many of you are computing background? And how many of you are neither electronics nor computing? Okay, very good. So, but you must know that, okay, everywhere in the world, you are going to use chips. Whatever you are doing, you're going to use chips. And a connected chip largely looks like this everywhere. So you have a computing. I mean, long time back when I started my career, we used to do electronic systems without a microprocessor in it. That means it will take inputs, okay, if you want to open the garage door when you're walking nearby, it will actually find out the proximity, then it will turn on the motor to open the door. Everything was done with electronic circuits without microcontrollers. But today people cannot imagine doing anything without microcontrollers. So microcontrollers have become cheap, they have become flexible, they become very powerful. So it's always there. And then you have to communicate, and that's the wireless connectivity portion within a chip. The thing that converts your ones and zeros into signals that go on the antenna. From the ones and zeros to the antenna radiation is the wireless part. And then you have lots of protocols of sending data to the internet. TCP/IP is the basic backbone. Then on top of that we have HTTP, HTTPS, MQTT, AMPP. So many protocols are there for different purposes. And you cannot avoid all of that. Part of the protocols live here, part of the protocols may be in your gateway. Sorry, I think this is a touch screen, right? Yes. How do I cancel whatever I did? Okay, go to full screen.
Yeah. Yes, I do
Control L, yeah. Yep. It's almost wireless, huh? I don't think I even touched it. Okay, so then it goes out somewhere. So the idea is that long time back, you would sense something, then you would analyze it, and then you will take an action. It is called a closed loop control system, which everybody studies in their college, control systems. Now they found out that a more intelligent or more useful decision can be done if you collect data from multiple sensors and take a better decision, be more aware. So how do you get all that data? Oh, from somewhere else it can come. It can be nearby, it can be in a different room, it can be something else. For example, if you want to know that you want to water your plants because the soil is too dry, the sensor will tell you that the soil is too dry. But then if you are subscribed to the weather report, and the weather report says that yes, it's going to rain in 2 hours, then you need not turn on your water. So your decision becomes more intelligent if you collect data from various sources. And when you collect data from various sources, you have this centralized place which is somewhere we don't know where it is. That's why you call it cloud. Cloud means behind the cloud we cannot see. So they use the symbol cloud to show, I don't know how it is reaching there, but somehow the data is going there. I don't even know where that server is. It only has, I know only IP address of the server, nothing else. It may be in Singapore, it can be in Bhopal, I don't know. There you can do the cloud computing, data analytics, and everything. And then you can send an intelligent decision back through the internet to the gateway, and the gateway sends a message back to your device, and the device can turn on the motor or turn off the fan or whatever. So the network control loop becomes enormous. It becomes very flexible, it becomes very powerful. Okay? And then as people went along, they found that, okay, if it is a simple if this then that, they can write the code. If it is something more complex, they don't know what to write. let us say that, okay, you are using an accelerometer. The devices have accelerometers. All your smartphones have accelerometers. You can do gestures. It will tell you whether the phone is upside down or straight way. If you move this way, it can detect through acceleration that if you take acceleration and then you integrate once over time, you get velocity. Once more over time, you get position. So using an accelerometer, you can determine what's going on. So let's say that you want to use an accelerator to find out that somebody has fallen down. That's an elderly person or a person in the hospital. How do you know he has fallen down and not sitting down in a chair? If you think about it logically, if you sit down, you will carefully sit down and carefully position yourself. If you fall down, suddenly you are letting gravity take effect. That means that you are going into a free fall situation. If you take a 3-axis accelerometer, it will be 0 in 2 axis, no acceleration. 1 axis will be 9.8 meters per second square. That is a gravity acceleration. When you're doing free fall, suddenly there is also 0. And then when you hit the floor, suddenly there is negative acceleration, spike. If somebody observes that acceleration graph, you will find that suddenly acceleration from 9.8 goes to 0, and then suddenly it goes negative. Okay. Then that means somebody has fallen. Okay, so this is the data you have over 2 seconds, 1,000 samples of accelerometer data you have. Now you write an algorithm to tell me whether somebody has fallen or somebody is jumping or somebody is sitting down. Fallen or not fallen? People don't know. It's very difficult. You can do it, but it's mathematically tough. So what do people do? They take the easy way out, the lazy way out. They'll put the accelerometer on 10 people, ask them to sit, stand, jump, fall. Every time they should say, oh, I sat, I fall. So you have a lot of data which is classified. Somebody has classified the data. And you feed that classified data to a machine learning algorithm, the algorithm will come magically. Suddenly when new data comes, with 98% accuracy, it will tell whether it is fallen or not fallen. Right? That is the power of AI/ML. We cannot do the algorithm, but through this, anybody can do it. You don't need to be a physicist or a mathematician to do it. But the downside of it is that algorithm which is created is complex. It has hundreds of nodes, so many multiplications and additions take place. You can optimize it, but it is still very large. So for that, people are using servers, they are using GPUs, all of those. But suppose there is no internet connection, can you find out whether somebody has fallen? You have to push the algorithm back into the device. And when you push it back into the device, it is called edge computing or edge machine learning. Okay, so this is all part of there in any system today, okay, at the device level. Okay, and the device itself contains all of this, and even within the device, specifically the wireless MCU or the microcontroller unit contains this. Sensors can be anything, gas sensors, anything. Sensors are usually outside. Okay, the actual wireless MCU, which is companies like Silicon Labs make it, Texas Instruments, NXP, TI, all Espressif, all of these companies, we make microcontrollers, not 16-core processors or Pentium class processors. No, these are energy efficient devices which clock speed may be 200 megahertz, 300 megahertz, not in gigahertz. Maximum 2 cores, not 16 cores. But this is what the world runs on. All the devices, whether it's a fast tag machine or the ECG monitor in the hospital, your refrigerator, everything runs on microcontrollers. Okay, and a microcontroller with a wireless interface integrated together is called a wireless MCU. Today, there is hardly any microcontroller without built-in wireless. Okay, earlier we had 8051. If you're a student, you have learned about 8051. They all had interfaces to which you can connect other wireless transceivers. Okay, but today everything is built in, and we are going to talk mainly about that. What's inside it is that you have the MCU with peripherals. You might have some sensors built in. Then you had an analog subsystem, a wireless subsystem, and an RF subsystem. All of these are needed to build it. So what's inside this MCU, this is also called a system on chip, is that you have a CPU, very important, you have memory, you have flash memory for storing the program, we have RAM for storing the intermediate values like variables and so on, or arrays, and whatever you are using to create it. And then you will have many interfaces, USB interface, I2C interface, I2S interface. Then you will have some timers. Most devices, 99% of the time, they are sleeping. My cell phone is sleeping, this is sleeping until I press something. They also have to do things periodically. Either they wake up because somebody has pressed some button and therefore an event has happened that you should wake up, or time is up, now I have to check for some messages again. So timers are very important. We have a lot of general purpose IOs. We have some analog IOs. Analog input comes as ADC. Analog output goes as DAC, D to A converter. And then you can create a lot of clocks for this. The higher the clock speed, the more is the power consumption. And wireless MCUs, like embedded MCUs, a lot of those systems run on a battery. So you have to conserve battery. So you have to be sleeping. If you are not using heavy computing, reduce the clock rate. Okay. And the wireless subsystem, which is doing the protocol, has a digital part and an analog part. Okay. The analog part is the ADC and DAC. The digital part does all the signal processing of conditioning the data, modulation, demodulation, error correction, and all of those. And you have some analog subsystem like power management, because you have so many voltages you have to create. From 3.3 volt input, you have to create 1.1, 1.2, 1.8. So many voltages you have to create very efficiently. So you need DC-DC converters. Then you have battery management, real-time clock, and so on. Okay. So I'm going to take example of one product from Silicon Labs called the SIWX917, which is a wireless MCU. It's got Wi-Fi and Bluetooth. Okay, 2.4 gigahertz. That is Wi-Fi 6 and Bluetooth low energy 5.4. It's got some memory, 672 KB RAM and so on. It also has an edge computing hardware. So when I say that machine learning, the inference is pushed to the device. Machine learning inference still takes hundreds of multiplications and additions. If you take a CPU, a processor, it has one multiplier. So every cycle, it can do no more than one multiplication or one addition. But if a machine learning thing uses a vector, you do a matrix inversion, you want to do hundreds of multiplications every cycle. For that, you need special hardware. So 917, like many of the emerging MCUs, has a hardware accelerator in which you can do machine learning inference without impacting battery life and doing it very quickly. So it has that also. And it has a lot of security. And my focus of my talk is to explain the security things inside. Okay, but the device is not just hardware. What I showed you as a block diagram is a hardware block diagram. There's a lot of software, and hardware we depict as a block diagram. So something is connected to something and so on. Software is usually depicted as a layer, many layers. Okay, this is a physical layer which is primarily hardware. Then you have the MAC layer, that is Wi-Fi MAC. Then you have a Bluetooth controller, and then you have a coax manager which controls both of them. Then you have the next level, which is the Wi-Fi stack and the Bluetooth stack. On top of that, we have the network stack, layer 3. Now you are coming to layer 3. Layer 1, layer 2, now you are layer 3. That is TCP, IP, UDP, HTTPS, and so on. Above that are the application part, like cloud agents and drivers. And finally, the end user application, which is an actual application. Read soil moisture level and see if it is more than this, you do this, or send this data there. It's what the user does with a microcontroller, whether he's building a refrigerator or he's building a ECG monitor. That what he is doing is here. The rest of all the protocols is provided by the device manufacturer, like Silicon Labs or NXP or ST Micro, so on. Okay, so given that all of these software things are there, where do we want security? Okay, Let's start with the lowest level. We are sending some data from here to a router somewhere. So if I keep an antenna there, I can also observe this. If I am talking to professor here, you can also listen, right? So how can you then protect the data that is being sent out? So it has to be encrypted. Okay, encrypted by a mechanism whose mechanism may be well known, but the key that is used for encryption must be known only to both of us, not to anybody else. So message encryption is important. The next is message integrity. What do you mean by message integrity? Correct. So the message, has it been tampered with? Or let us say that you are getting some random data. If you assume that it has been encrypted with the key that I know, you will try to decrypt it. In any system, if you feed data, you will get some data out. No system says there is no data out. You will get some data. Because it's random, you will get random output. And then you might try to interpret the random output. Oh, here it says that turn on the fan. You go and turn on the fan. It's all junk. And that is how you can attack a system also, by giving some wrong data. So you need to have a signature which only I can create. The whole world can know that yes, this is his signature, but only I can create it, because I only have the private key to do that. Okay. So when I create it with my private key, others with their public key, then they derive it, and then they find that this key is derived from the message contents. So the message content modified in some way, in a way in which I only know, is the signature. And then when you decrypt the signature using a public key, and then you can compare it with the message content, you will find that it matches. Yes, this is a hash of this particular message, and therefore nobody has tampered with this message. Okay. So that is message integrity. Then you also have something called device authentication. Who is sending the data? Okay. Every device is known by its MAC address usually. Okay. If I see the MAC address, then can I be sure that it is he who is sending it to me? It cannot be, because MAC addresses can be spoofed. Okay. So there are other ways to figure out device authentication. I'll talk about it. Then you go to the next level, which is the IP layer. This is the MAC layer. From here to the access point, transaction is over. I'm only worried about who is putting an antenna and reading this signal, right? And then you go to the network layer. Now network layer goes on the internet throughout the world. That packet is sent from router to router, maybe from here to California, from California to Iceland. We don't know where it goes. But all of them again need encryption, integrity, and authentication. Now, instead of the device being authenticated, you want to know that you are sending it to the right destination. So you want to authenticate the server. And that is what is HTTPS or TLS, what our previous speaker Vishal mentioned. You have to know that you are sending it to the right one, because if you go to some websites, you will get a message, we could not authenticate this particular website. Be careful. Do you still want to open the connection? So you have to figure out that you are sending it to the right person, and then you have to do encryption and integrity all over again. This is a different mechanism compared to this. Okay, this is all for communication. But what about the device itself? We have something called secure attestation. That is this device, okay, what it is claiming to be? How can we be sure that I am talking to the right device? Okay. Then you have a secure zone, which means that nobody can tamper with the software in this zone. This is protected. Okay. So if somebody tampers with the software, anything can be done. If you download a virus without protection, anything can happen. Okay. Then you have encrypted execution. Then you have encrypted key storage and encrypted firmware upgrade. I will explain it, okay, in further slides. Okay, so let's start with the application layer. Let's start with secure firmware upgrade. Every day, every week, whenever you open a device, it will say firmware upgrade is available. Can I download it now? Or do you want to download it at 8 p.m.? Every device, whether it's a cell phone, whether it's your TV, whether it's your refrigerator, any device, you will keep getting firmware upgrades. Why? Why do you get firmware upgrades?
Latest security patches.
Well, latest security patches also is correct. New features also okay. But the number one reason is that there are bugs. No engineer makes a software without bugs. Every software will have bugs. Some software will have hundreds of bugs, some will have dozens of bugs. So you have to keep fixing it. You cannot wait till all the bugs are fixed. By the time, the general manager of the company will retire. You have to keep sending. And then you keep doing firmware upgrade. Right? But then you become vulnerable. Suddenly you get a message, latest firmware upgrade available. It solves all security, new features, brand new features are available. Download now. And then you download, what will happen? You don't even know what is there inside. So protecting a firmware upgrade is very important. So you have to actually establish a secure connection with an authenticated server. No firmware should be downloaded from any server which is not authenticated. How do you authenticate a server? Use a trusted security certificate authority. That means that somebody you trust has given a certificate to this server. And when this guy gives you his certificate, you go and ask that authority, hey, I got this certificate, is it okay? That guy will tell you, you apply this particular public key, and then look at it, then if it passes, then that server is okay. So there are some people who actually verify the certificate for you. So you go to that server after authenticating it, then you take a firmware which is encrypted, because if the firmware is not encrypted, it is difficult to figure out whether any tampering has happened. Then you have to digitally sign it. That server will sign that firmware digitally. Finally, the device will decrypt the image. It will verify which version it is and so on. It will verify the signature. Everything is good. Then now it can upgrade. No, it will do one more check. The version should be newer. If somebody sends you older version with known security problem, everything passes. So authentication server passes, signature passes, decryption passes, everything passes. But suddenly instead of 1.3 you're already running, now it becomes 1.2. Now what will happen? Your device will be vulnerable to some security vulnerability which was fixed in 1.3. So you cannot downgrade also. So after doing all of those checks, then the device will replace the current firmware with the new firmware. So all these mechanisms are built in. Now the second thing is, you have, let's say I have a Wi-Fi password. So next time I connect to the Wi-Fi, next time I don't have to enter password again. It's already stored in the device. So next time I turn it on, it will connect again. All your laptops do it. But suppose I grab somebody's device. Suppose somebody has a IoT device in his gate. I steal that security camera, open it, one flash memory is there. I'll take that flash memory and put it in a reader. Then I'll get his Wi-Fi password. Right? Because Wi-Fi password is stored. But we don't want to do that. We want to encrypt it and store it. So if the device falls into unauthorized hands, then the decryption, you will not be able to decrypt it. But what will happen if the decryption key and everything is stored in flash? You have to decrypt it. Decryption also requires a key. Where will you keep it? Also in flash. So anything that is stored in flash is readable. So there is a mechanism called a physical unclonable function which will generate a signature for each device. It's like, what is a device signature? It's like a fingerprint. Every person has a unique fingerprint. Even if they are identical twins, the fingerprints are different. So what they found out is that when you are making thousands and thousands of chips from a silicon wafer, the physical nature of the wafer is such that no two chips are exactly the same down to the transistor atomic level. So you have often come across memory that is not initialized. You take random access memory, you power it on, okay, when you power it on, you don't know what is there. You keep writing something in it, then it is initialized. Okay, sometimes you have a variable in your C program, you take an array and initialize that array to 0. Because if you don't initialize the array to 0 and suddenly start using it, if this one is 5, maybe it will be 5. Because if you don't initialize RAM, nobody knows what it is. What they found out is that if you have a RAM, randomly, because of the physical nature of the device, it takes a certain set of values. And another device created from the same silicon wafer may not have the same set of initial values. Because down at the atomic level, the two things are slightly different. There are some minor temperature variation when the manufacturing happened. The physical nature of the silicon is slightly different. Okay, so if you take a large array of memory and two different chips, just do a power on, they will have different values. And then they also found that these values tend to repeat to at least 70% extent from every power on to another power on. So that random value can be the digital signature of that device. And you create a key using that signature and then encrypt the flash. So when you want to decrypt it, you feed that key, the data, and the decryption will happen by the key that is generated from the RAM. And then it will give you the plain text. Now when you power off the device, there is no key because the key is generated on the fly. You don't even know what the key is. The key is taken into this system, key is applied, encryption happens, decryption happens, and then the result is given to you. Okay? So using this function, you can, our devices have it, many other devices also have it. You don't have to store keys. You can actually store encrypted key, and the key to decrypt that encrypted key is not stored in the flash. That is the concept. Okay, so this is the principle I told you about a little bit early. From the SRAM, you take that random data, you do error correction and find a device fingerprint, and then you can use that fingerprint to create a number of unique codes which you can use. So from that random data, you can get code 1, code 2, code 3 by using different combinations of those bits. You know that all that codes every time will be different. I mean, every time you power on, it will be the same, but among the code, they'll all be different codes. Okay, the keys can be created and then you can use it. Okay, so another concept is called execute in place. If you have your executable data in flash, that is your program in flash, then if somebody grabs the flash, he can read that object file and then he can generate assembly code out of it, and from assembly code he can even generate the C code out of it. So all your effort in doing something, now somebody can copy your device. Okay, and all your R&D that you have done, somebody can grab it. So how do you prevent that? It's by encrypting the code that is there in flash. However, the encrypted object code, if you take it and give it to the processor won't understand it. So you have to take the encrypted code, you have to decrypt it and then pass it on to the flash. So because these codes for encryption and decryption are locally generated through the puff logic, while giving a firmware upgrade, the server cannot send an encrypted file. It might send an encrypted file, but that encrypted file is first decrypted using over-the-air firmware upgrade key. And having gotten the decrypted firmware, it is stored in a temporary location. From the temporary location, it is read out, and the device-specific code, which nobody else knows about, is used, and the encrypted code is stored in flash, and this flash is the one which is used to take data and send to the processor. Instruction by instruction, the next instruction will come, it will get decrypted and sent to the processor. So the flash memory can contain encrypted code. Okay, so ARM has something called trust zone, we call it secure zone. So let's say that you have two processors. One processor which we program, chip vendor programs for doing the network protocol and everything. And then there's another processor where the user writes application, the refrigerator application, okay, the pulse rate monitoring application, whatever it is that they are doing, maybe that remote clicker application. This also has a microcontroller, right? This also sends wirelessly. This is also a wireless MCU based device, right? So, but the RAM is usually shared, because for depending on the application, you can open more RAM, less RAM, and everything. So, and you also need, this application will create some data, one array, which has to be sent to the server after being put in a packet format by the second processor. So, portions of the memory must need to be shared. So, but there is also some protection there. There is also your code and there is open code. So, what is allowed is that this shared memory can be accessed by both, whereas this protected memory can only be accessed by the vendor's core or the vendor's portion of the logic, okay? And the processor which is doing application code cannot access this. So, this is called a trust zone or a secure zone to make sure that you write a program to corrupt the way TCP/IP is handled. If you go and corrupt this portion, then communication may fail. So, you can write some application which will make sure that your refrigerator will no longer now work well. You can go and corrupt it. Okay? It can happen intentionally or it can happen by accident also. Very often it happens by accident. Like I told you, every software engineer puts bugs. Because of a bug, he has gone and corrupted that other TCP/IP code. So now the device is unusable. How can you do firmware upgrade? You cannot. TCP/IP is not working. How will you get it? You cannot get it. The device is scrapped. So the service engineer will come and he'll say, oh, the control panel is gone, you have to replace it. He will charge 5,000 rupees and replace control panel. Why? Because some software engineer had a bug in it. Right? So you want to protect against all of that. And you're doing all of this. Okay, and this is a concept called secure zone. Okay, and the secure attestation, I didn't talk about that, but secure attestation is, are you the device that you're talking about? I spoke about the physical unclonable function, which has a unique fingerprint of each device. So whenever the device is manufactured, its fingerprint is recorded in a secure server. So if I am manufacturing, suppose let us say I'm a manufacturer of smart TVs. I want microcontrollers, 1 million microcontrollers for my 1 million TVs. So I will tell the chip vendor, you give me the signatures of all of those 1 million chips that you're going to give me. In a very secure storage way, as they're manufacturing, they'll take the signature and give you. And now when I want to push firmware upgrades or I want to read the device status, I can look at the signature and compare with my database, and then I can know that yes, this is one of my devices. This is not somebody else's device. Because the same chip vendor, he can sell to Samsung, he can sell it to Panasonic also. Right? If Samsung has a new feature, I cannot take and download firmware from Panasonic and put it on my TV and get Panasonic features. The manufacturers want to protect it themselves. Right? That is secure attestation. Okay, now let's look at the network stack a little bit. Now, everybody now today, most websites are using TLS. That means they use HTTPS, S for secure. Okay, so why do they need it? First of all, we don't want anyone to give wrong data to us. If they give wrong data, then our devices will stop working, will do crazy stuff. And there are a lot of people who want to, denial of service. They want to make sure that services are disrupted. Okay, so or sometimes somebody can pretend to be the client or somebody can pretend to be the server and try to establish a new connection with new keys, and then try to, whatever this guy is trying to send, it accepts it. That's why, in an analogy, if you go to a banking website, it will ask you to verify a particular picture or something that you have put there. So only if your picture comes there, then you can be sure that it is really the bank site and not somebody mimicking the GUI of that. So if you mimic a GUI of, say, HDFC Bank site, then anyone who sees it may think it's HDFC Bank. So they have actually put another picture which you have chosen at the time of setting up the account. So how do they know your account? They don't. So they may not put that picture there, right? So similarly, you have to make sure that they are not pretending to be one. So how does that TLS, earlier it was called SSL, by the way, if you come across the term SSL, remember that today it is called TLS. Okay, how do they do it? So they use cryptography for encryption. It can be either symmetric or asymmetric. Asymmetric is public key is different from private key. In symmetric, both keys are identical. Where is public key used? Is in many of the transactions where you want to authenticate the server actually puts data encrypted with a private key, and it freely shares the public key to you. So the data is not the information from the website is not confidential. If anybody has a public key, they can decrypt it. But the identity of that server must be authenticated. So when you decode the signature using the public key and you get a certificate, it should match that particular device's certificate. So the public key encryption is there all over the place. RSA is there, Diffie-Hellman is there. Okay, you heard about all of this. Then you have encryption. Most common today being Advanced Encryption Standard 128. It's called Galva-Cold multiplier. There are many other. Triple DES was used for a long time until it got replaced by AES. So for encryption, you have some algorithms. Then for message integrity, you can actually, that is the signature. Like the signature is actually a hash of the message. Okay, our signatures are the same no matter what the document is. Digital signatures are different. They are different for different message content. Okay, so if the message changes, the signature also changes. And they used hashing techniques for doing that. There are so many hashing techniques are available, MD5, SHA, and so on. Okay, and then you use the public key infrastructure for doing the authentication. So encryption, integrity of the message, make sure that nobody has interfered and changed a 1 to 0. If you change some bytes in the message, signature will now mismatch. Okay, so decryption will happen, everything will happen. But how do you know that somebody has removed 2 bytes and put new 2 bytes there? Okay, the integrity will fail. Okay. So all of these are needed for at the network layer. Okay, so but how do they? I already spoke about this. How they do it? But to tell you, okay, there is a certificate authority who is well known, and I trust him. The client or the end product trusts that certificate authority. Okay, so certificate authority is the one who will issue a certificate to a server. And is this certificate accurate? That can be verified because you trust him. You can go back and check, is this certificate you have given to so and so or not? Okay, and then the certificate authority says yes, or gives you a mechanism in which you can verify it. Then you can make sure that the server is whoever he is pretending to be. Okay, now let's come down to the MAC layer. So whenever you start a wireless or Wi-Fi connection, you start with something called a password. Password is what, like that NITK something something XYZ, you have to feed the password. That becomes an initial key. It's also known as a pre-shared key. Okay, and that key can technically be used to encrypt all the data. But the problem with that is that people who are trying to hack or figure out what the data is, if you are given thousands of messages encrypted using the same key, sooner or later you can figure it out. That's why the previous speaker also said that quantum computing techniques, can, because of the nature of the qubit, it can simultaneously exist in 4 states. It can test 4 of them at the same time. It can simultaneously exist in 20 states. It can test 20 alternatives at the same time. And therefore, it is 20 times faster, 100 times faster. And you have to protect yourself against it. So one way of countering that is that you keep changing the key. Every 30 seconds, you change the key. Every 1 minute, you change the key. So you are creating dynamic keys periodically. So you start with the pre-shared key or the password, also called a pairwise master key. This key could be for each pair, but in most of the normal Wi-Fi communication, everybody uses the same password. There is something called enterprise Wi-Fi connection, in which every person has a different password. Both are possible. But so the pairwise temporal key, which is a dynamic key, is derived through a process called a 4-way handshake. That 4-way handshake is, how do you alter it? Every time you alter it should not be the same way that you altered it earlier. Then also people can guess. Getting from your password, getting a temporary key, that should not be a very straightforward process which repeats every time you power on a device. So they use something, they mix the key with some random data called a nonce. Nonce means number used only once. It's a random number. Every time it has to be a different random number, and it's not easy to create random numbers. And there are special hardware device modules which are used to create truly random numbers, and that is what is needed. Otherwise, most cases, if you put one R&D function in your C code or Python code, it's not a real random number, it's a pseudo random number. That means that it can be repeated. If you change the whatever is the initialization thing, seeding it's called. For the same seed, it will give the same number only. So it's not that secure. So any case, one method is to keep on changing the key. And the algorithm itself, so key management is one part. The second is the actual encryption, which wireless LAN uses AES, Advanced Encryption Standard, 128-bit. It's a symmetric cipher, that means both sides use the same key. And this AES works on something called a substitution permutation network principle. It keeps changing the data, randomly shuffling. A certain way it is shuffling based on the key. Again shuffle one more time, again shuffle one more time. So from the end result, it is almost impossible to go back and figure out how the data was created, because the shuffling is so random. And then finally you have a message integrity check. Remember that every message has to be authenticated. The integrity of the message. If somebody modifies some bytes, that fact that it is modified must be known. So there is a message integrity check that is used there, which is again derived from the same AES. It's called a CBC MAC or cipher block chaining message authentication code. It is added to the data. I am not talking about how it is generated. There is some mathematics behind it, but message integrity also is done. And as wireless LAN becomes, as quantum computing comes in, they have told the 802.11, IEEE 802.11, which defined the wireless LAN standard, said that by 2036, this should be changed. It should be changed to post-quantum cryptography. And there are many candidates being discussed, one of them being called MLKEM.
It got disrupted internet.
Okay,
So
sure.
we will
Sure. So he's just fixing the internet. But what they said is that by 2036, your cipher should be modified to be post-quantum secure. And by the way, if you search for IEEE 802.11, and there are working groups which are trying to figure out what should be the encryption standard, And that information is open to all. If you want, you can also participate in it. If you want, you can also propose your own mechanism. You can read what others have done. It's all completely open, and you can join that group, and you can be part of the process of defining the next standard. It's open to everybody. While we are waiting, I can, Yeah. While you are waiting, I can take questions locally, if you have any. Yeah. 802.11, which is our Wi-Fi standard. Wi-Fi is a name given by another organization called Wi-Fi Alliance. It is to make sure that everybody is familiar with it, but the standard is defined by IEEE. Okay, so for IEEE 802.11. Yeah. Yeah. Yeah.
You told that there is a signature during the manufacture only.
Yep.
They will give the signature.
Yes.
If I am sending some data from my computer to one server, we know that it will follow some routers and it will reach the server and I will get back.
Yeah.
While getting back only, I can get the MAC address along with the whatever the signature you told. At the end user side, I can get.
It's the end user's signature that is needed. Let us say that, okay, you are.
No, I need the information about complete path.
No. You establish the identity of a device.
Yes.
During the establishment of a connection. If you identified that, let's say that you are sitting in the cloud. You are a software. Okay. You are trying to access data from a particular device. It is giving you some data whether somebody has come into your house or not come into your house, let us say, right? You want to know that somebody is not spoofing your device, saying that don't worry, nobody has gone into your house, while the real device is deactivated and somebody has gone into your house. Okay, if somebody says nobody is there in the house, I want to know that I am querying the right device. So how do I figure out that it is the right device? If I ask for the MAC address, maybe the MAC address can also be spoofed. But if I verify the signature, that signature is unique to your device, which he doesn't know. So he cannot recreate that signature. So I know that I am now addressing a wrong device because signature didn't match.
No, any community throughout the internet, they have an authentication for the routers only. I'm asking routers, gateways.
No, device authentication is what we are talking about. Router authentication, server authentication is there.
Okay, server is
HTTPS
there.
and everything we spoke about. But if you want to identify the device, how do you do it? That is where the unique device fingerprinting is helping. It's like how do they do your Aadhaar? They use your fingerprint.
Yes.
Same. How do you verify that is the device I kept in my house? That device should have a unique fingerprint. Otherwise, somebody else can copy the entire device, every bit in the flash, everything can be cloned.
No, whether attackers can get the whatever you told that in the flash also will make encrypted type of signatures. Whether they can get that thing also, at least.
Let them suppose they get encrypted one. Okay, if you don't have unique device code, then two devices are identical. If the flash is encrypted, the key is also stored. So you can clone the complete device and it will look just like this device. Okay. So if you can completely recreate the device by copying every bit of the flash and putting there without any change. If you do that, that device will look like this device. And now, since you are controlling that device, you can now send whatever message you want. To prevent that, you have a device level fingerprint, which even if you copy all the flash content, that fingerprint is generated at runtime. So it cannot be predicted, it cannot be reproduced.
And another thing, just now you told that when you are connecting to Wi-Fi, generally we'll use one password. You told that multi-level password also. Can you highlight how?
For example, here you have one more authentication layer where you're connected to the Wi-Fi, but you still cannot connect to the internet unless you are given your credentials, maybe your college roll number or your guest house number or hotel room number. So that's a second level of authentication. So there also it is just a password based.
Okay.
So just 2 levels, so that if you share your password with somebody else, then he should not be able to freely start using it. It's just one more level of security.
Okay,
You can
sir.
always share with him the whole thing, then he can also use it. So this to some extent can.
So I have a
Ah, yeah.
You talked about signature. So are we creating some sort of hash and that we are treating as a signature? Hash
Yes.
of the information.
Yes. So like I said, when we sign a document, our sign is the same for all documents. In a digital signature, you take a hash of the memory message and then you add some other stuff to it. So if there is anything changing in the document, now here visually we can see, oh, somebody is pampered. So there, if somebody modifies some 2 bytes, then the signature will fail. So that is the reason for hashing that. Okay, hashing that means, okay, from the entire thing you bring it down to 16 bits or whatever, right? From 16 bits you cannot get the whole thing. So the reverse hash doesn't work. All right, so we spoke about all of this. I don't know how many the online folks have missed, but at the end we'll have some Q&A. Okay, so we do all of these things, and I told you that devices need long battery life. Nobody will like this device if its battery life is only 45 minutes, because a typical presentation, once you ask a presenter to talk, he is not going to leave the stage for at least 1 hour, right? So battery life is extremely important. What they figured out is that if you are using a microcontroller with 1 arithmetic logic unit and then you are doing thousands of mathematical operations on it, then it consumes a lot of energy. Every time you add data to memory, every time you read data from memory, energy is lost. So a lot of techniques are there for firmware engineers to increase battery life by reducing memory accesses and everything else. But even better is to do things which are, you give a dedicated hardware with say 500 multipliers, okay, or at least 10 multipliers. So things can become much faster, so you can have hardware accelerators which will do crypto functions. So we have a lot of hardware encryption functions in hardware. So you call a function that will go out through an interface, that device will get back, that will finish that operation much faster than doing it in software. The other thing which is required in hardware is the true random number generation. Like I told you, everything else is pseudo random. So true hardware random number generators use thermal noise. So when you just look at this temperature based Gaussian noise, right, it's truly random, you can use that. Or you can use the metastability of digital circuit, like I told you about the fact that a digital circuit, when you don't initialize it, can be something 1 or a 0 or whatever, okay, and you can use it randomly. You can use quantum effects to create randomness. You can create a ring oscillator, and then you can look at the jitter on it, which varies even at the same temperature, it will keep varying. Okay, so there are many physical phenomena that are used to create true random number generation. It's not just a ones and zeros, there are some analog circuits involved here. Okay, so inside our chip, you have a lot of hardware functions which are a lot of functions which are in hardware. Okay, the puff is hardware, true random number generation, SHA, AES, so many crypto functions are all in hardware, so that you conserve power and do your job faster. Okay, so finally, in summary, the IoT products, we are all calling them as wireless MCUs. Today, hardly there is any microcontroller without a built-in wireless interface. Everything needs it. One of the biggest markets for the 8051 microcontroller early on was the keyboard. The keyboard had a microcontroller. People were amazed. Microprocessor itself was rare in the PC. The keyboard has its own microcontroller, right? So, but today everything is wireless. So whatever microcontrollers do, interface has to be wireless. So that's why they're called wireless MCUs. And next few years, all microcontrollers will also have a hardware accelerator. Then security is needed and applied in all stages, protection of data, making sure identity is verified correctly, and protection from malicious software uploads and downloads are all part of what is needed in any IoT device. Okay, and this is what we spoke about. All right, so this is my email, nvenkatesh@ieee.org. Easier than my Silicon Labs email, which is very long. So I always respond to all emails. So if you have anything, you can always write to me at any time. All right, so I think we have 6 minutes for Q&A. And anyone online missed something, you can ask now. I don't know how they can talk.
Yeah.
Okay.
Do we have IoT search engines?
IoT what?
Search engines.
Search engine.
If there are some 10,000 IoT devices,
Ah.
each one of them they will be placed in a different place
Yeah.
for different purposes.
Yeah.
Then how it picks up and identifies? A query when it is put,
Okay.
how it aggregates, and now you told from one single IoT point of view.
Yeah.
So IoT search engine concept, anything is
So no, what you have hundreds of IoT devices. Let us say that you have a field in which you are measuring the soil moisture, and you have say 100 IoT devices in the field. Now each device is known by a certain identity, and the location of each
Location.
device. Okay, it can be either programmed, either marked by hand. That means when you are placing it there, you use a software application to say that in position 71, I have this one. The other way is to find out through proximity where it is. One of the ways of locating a device is by looking at the signal strength to the access point. You find the signal strength from 3 different access points, you can trilaterate and find out. That is one way. The other way people are doing is something called angle of arrival. The access point will have multiple antennas. When you are sending a data, using multiple antennas and the phase changes, they can identify the direction. And if they identify the direction from this one and this one, then they can pinpoint where it is. So angle-based locationing is also available. The third method is they use something called time of flight. That is how many nanoseconds is taking for data from this device to this. If you go 3 meters away, it will be 3 more nanoseconds. So you can find the distance by doing time of flight measurements, and then you can trilaterate with that.
time continuous, time discontinuous. Some of the IoTs will have some thresholds to give the value. So certain thresholded value only has to be picked from that search engine.
Sure, I mean you can actually put local.
Is it a computer science person's job or?
That's it. See, basically, let us say that IoT device, you have 100 devices. Every
1,000.
minute, 1,000 of them.
Yeah.
Every 2 seconds, they are reading data. You don't want 2,000 data every minute
Yes.
if the data is not changing. So you can figure out, you can put logic there, not to send if the data is not changing. Other things that can be done is that you can figure out that these 2 IoT devices seem to be correlated. Somehow same measurement is coming here also because of their proximity or whatever. Then at the router level, you can discard one and send only one. That will reduce the traffic further on.
Any middleware will be there?
You're talking about errors?
In search engines,
Ah.
any middleware will be there to sort out all these things and then send it to the final place.
It's all somebody's logical software which has to do it.
Okay. Sir.
There are no standard ways.
Yeah.
People have to write it.
Sir, again at the router level, when the data aggregation is happening, again it will consume energy, right?
Correct. So if her question was that at the router gets lot of data from lot of IoT devices,
Yes, sir.
then router also consumes lot of energy. Well, okay, the way things are is that today routers are not battery powered. Okay, routers are on all the time. Okay, to conserve battery, you have to be sleeping maximum time. But the routers cannot sleep because any time IoT device can send data to it.
Yes, sir.
So routers are not energy efficient in the sense that they are always on devices. Okay, so
But usually that aggregation happens at cluster head, and the cluster head does not, it is battery powered only, right?
well, if you are talking about any device that has to be on all the time, then it cannot be very battery efficient. Okay, battery efficiency comes primarily from turning off when not needed. If there is a say border router, if you have
Sleep
a mesh,
mode and-
if you have a mesh network, this particular node should forward the messages, then this node cannot sleep. Right? So any node which should receive all the time cannot actually run on battery, without having to change it every day. Okay? So people use the architecture of the network based on what they want to do, and then they decide which one can be battery powered and which one cannot be. Anyone online?
Hello, sir. So you said the microcontrollers will get some hardware accelerators. So what are these accelerators, by the way? How does it work? And is it similar to the working of a GPU?
Correct. So a GPU is also an accelerator. What the GPU came was that they found out that if you are doing a graphics card, you have to update the pixels. Now you have to update all the pixels, 1 million pixels, let us say. If you want to update 1 lakh pixels or something, then the CPU has to go and update everyone.
Correct.
That makes it very slow.
Correct.
So the graphics accelerator does the computation parallelly and updates all the pixels immediately. The computation, the CPU has only one multiplier.
Correct.
The GPU has got hundreds of multipliers, hundreds of accumulators.
Okay.
So this is an example of acceleration. And all accelerators are a collection of multipliers and adders.
Okay.
How you configure it, how you can address it, how you can retrieve data from it, they are all different. But core of any accelerator is lots of multipliers and how they are connected to each other.